Okay, so last class we talked about precision versus accuracy, and we said that our goal is to make our measurements precise and accurate, right? Now, we need significant figures so that we will not make too much or we will not overstate the accuracy. You see that sometimes when you do calculations in your calculator, you will get like all 10 digits, right? If you start writing down all those 10 digits in all your calculations, just imagine first of all how tedious that is going to be, and you are overstating the accuracy. We don't need up to the 10th digit accuracy in our calculations. And maybe you kept it that way, but he did not keep it that way. So at the end, you will end up with two different answers. So in order to be on same page with our calculations, we are going to use significant figure rules when rounding off. So let's just look at what are the rules. So the first rule is that all non-zero digits we see in a number are significant. All non-zero digit. Now, zeros between two significant figures are themselves significant. So let's say, for example, let's say there is a number here, 9421. This number doesn't contain any zero. All are non-zero digits. So we are going to say this number has 4 significant digits. Okay, all 4 numbers are significant. Now, how about 94021? Well, there is a 0 in there, but it is between two significant figures, right? 4 is a significant figure, 2 is a significant figure, and that 0 is in between. That means this 0 also will become significant. So this number contains total 5 significant digits. Okay? 1, 2, 3, 4, 5. All 5 are significant. See the difference between rule number 1 and 2? Okay. Now, zeros at the beginning of a number are never significant. What do we mean by that? Let's look at another number now. 0.00940021. Here is another number. Okay. Now, how many significant digits are there in that number? 5 is correct. These zeros you see at the beginning of a number, they are never significant. It doesn't matter I have 2 zeros here or 3 here or 10 here. They are not significant. Only this is the first significant figure in this number, and from here onwards, yes, they are all significant. So still we have only 5 significant figures in this number. Is that rule clear? Now the last rule, zeros at the end of a number are significant if a decimal point is written in the number. So let's consider another number. I'm going to give you an example. So 9421.0 and then just 9421. How many significant figures in the first number? How many significant figures in the second number?
5.
The second one, yes, definitely we all agree with that. There are only 4. The first one, 9421.0. This 0 is significant. Read this rule, number 4 again. Zeros at the end of a number are significant if a decimal point is written in the number. Okay? So we have a decimal point, therefore this 0 is significant. So if you have to write total number of significant digits in this number, it should be 1, 2, 3, 4, 5.
If there's another 0,
Then it would be another 1, yes.
it's still the same.
yes, it would still be significant. It is when zeros are not counted is only when it is at the beginning of a number. In the middle, it will count if this zero, look at this zero, this is in the middle. If it is in the middle of two significant figures, they will count. Okay? So these 4 rules. Again, first rule, all non-zero digits are significant. So to illustrate that, one more example, that is, let's say 0 point, no, not 0 point, guys. I want another number. Let me try it, oops. Let's say 10 point 1 2 0 3 4 0 0. Let's count the significant figures in that number.
7.
Okay, I hear one choice 7. Is there any other choices? I hear 9. Anything else? Either 7 or 9. That's our choices? Okay. Let's look at the rules again. Is there any zeros in the beginning of the number? No. So rule number 2 doesn't apply. Oh, sorry. Rule number 3 doesn't apply. How about rule number 2? Zeros between two significant figures are themselves significant. So we see zeros between numbers. Let's say this 0 and this 0. Are they going to count? They are going to count, right? According to rule number 2. Oops. The pen is extremely sensitive today. Now, rule number 4, zeros at the end of a number are significant if a decimal point is written in the number. Is this number has a decimal point? Yes, it has. Therefore, are we going to count the last 2 zeros? We are. We are counting. So that means this number has 1, 2, 3, 4, 5, 6, 7, 8, 9 significant digits. Questions on significant digits so far? Okay, now once we learn what are significant digits and what are the rules to follow, now we are going to learn additional principles. How do we use them in calculations? When we perform addition or subtraction, the rule is that answers are rounded to the least significant decimal place. So here is an example. We want to do an addition. Let's add 12.321 and 3.13. These are the two numbers we want to add. Normally, if you perform your addition, you are going to say 1 and 3 plus 2, 5, 3 plus 1, 4. Here is the decimal point. 3 plus 2, 5 and 1. Right? Okay. According to the significant digits rule of addition and subtraction, we can't leave this as our answer. We have to round it off to the least number of decimal places. What do we mean by that? The first number after the decimal point, you have 3 places. Right? In the second number after the decimal point, you have only 2 places. So which one has the least number of decimal places? The second number, only 2. So you have to round it off to 2. 2 decimal places, your answer. So if you have to round it off to 2 decimal places, you are looking at 0.451. What do you do with this 1? Just say goodbye to that 1. Let's say, for example, when you did this, you had, instead of 1, this was a 7. Then what would you do? Then round this 5 to 6. You know that, right? When you're rounding off anything equal to 5 or above, you will say goodbye but add 1 to the previous number. Anything below 5, you will just neglect it or let it go. Okay? So this is the rule for addition or subtraction. Now when it comes to multiplication or division, the rule is different. Answers are rounded to the number of digits that corresponds to the least number of significant figures in any of the numbers used in the calculation. So here is an example. We want to multiply 3.0, 12.214 and 1.22. I don't know what the answer is, doesn't matter. You can do the answer, I just made up the numbers. So if you are doing this multiplication, okay, just for the sake of it, go ahead, somebody pick up the calculator and punch in these numbers and give me what do you see on the calculator screen. Don't do any roundups. Just give me the number. $70324. Okay, this is what you see as the answer. Now the rule, let's read the rule one more time. It says, when multiplication or division is performed, answers are rounded to the number of digits that corresponds to the least number of significant figures in any of the numbers used in the calculation. We are not talking about anything specific to the decimal places. We are talking about the whole number. Okay? Now these are the three numbers we multiplied. The first number has how many significant digits?
1,
2. Do not forget the decimal point. The 0 is after the decimal point, so it does count. How many this number has? 5. How many this number has? 3. Which is the least number? 2. So your answer should be rounded off to just 2 decimal points. That means the 7, this is the first two significant figures or first two decimal places. Now we have to say goodbye to everything after the decimal point, but we are going to round off and this is a 7. So what do we do? Your answer should be expressed as just 35. These are the rules for significant figures, rules for multiplication, division in using significant figures. Is this clear?
How do we know it's 34 point something, something, something?
That's what your calculator gave.
I got 44.7.
Well, 34, 44, I don't know. Somebody just gave me the number and as I said, it doesn't matter what exactly that number was. Of course, it would matter if you're doing a real calculation. Here my point is just to show you the significant digits rule. Was it 34 or 44?
44.
It's 44. Okay. If it is 44, then your answer will be 45. Question so far? Yes.
But what if your answer is like 473 point something?
400 and
Anything like in the hundreds place.
473, something like that?
Yeah.
Okay, we are going to learn one more thing now. Something called scientific notation. When we have numbers like that, we have scientific notation and we can express this number as 4 into 10 to the power 3. So that, well, we need 2 significant digits, right? So that means, 4 into 10 to the power 3. Yeah, that would be the rounding off. What I'm trying to say is if you write 40 into 10 to the power 2, this will be your number according to the significant digits, but then comes a scientific notation rule. This part should be a number between 1 and 10. It cannot be more than 10. So you will rewrite that as 40 into 10 to the power 3.
So you could do 4.0 to make it 2 cents.
4, you can kind of write, 4.0 into 10 to the power 3. Yeah, that will make it 2. Yeah.
Why can't we just keep it
the 44.70324. That's what I said. If you start keeping that number, you can imagine there is a calculation with 10 steps, and at the end, you know, you are overstating your accuracy, or different people would come up with different numbers. That is why we need the common rules to follow the steps. Okay? Questions so far? We are good? So next thing we are going to look at is dimensional analysis. This is not only important in chemistry. If you are taking math, physics, chemistry, or even biology problems, anywhere you have to solve problems or convert units, you will need dimensional analysis. Okay? So we are going to learn how do we use dimensional analysis, or what it is. So we use this to convert one quantity to another quantity. We will have to do this very often, especially in physics and chemistry, converting one quantity to another. So one important thing we need for any dimensional analysis is conversion factors. Conversion factors means it is a fraction, something expressed in the form of a fraction. It's the same quantity but expressed in two different units. That's all conversion factor means. So say for example, we know this for sure. 1 inch is 2.54 centimeters. Right? We know that. 1 inch means it's 2.54 centimeters. Now, if we are given a quantity in meters and we want to convert that to inches, what would you do? We don't have any direct conversion between meters and inches. You don't know how many inches is 1 meter, right? But all you know is 1 inch is 2.54 centimeter. So first what you will do is you will convert the meters to centimeters using a conversion factor. How many centimeters are there in 1 meter? 100. So we can use that as the first conversion here. That is why 1 centimeter per 10 to the power negative 2 meters, or 1 meter is 100 centimeter. They are one and the same. Once you get the centimeter, you can use this conversion factor to convert this into inches. So as it is written here, this conversion factor, 1 inch is 2.54 centimeter. You can express that in two different forms, either 1 inch over 2.54 centimeter or 2.54 centimeter over 1 inch. How do you decide which form should be used in the calculation? There is something which we can look for so that we won't make a mistake. Here is the hint. When we use the dimensional analysis, use the form of the conversion factor that will put the sort out unit in the numerator and whatever unit you are given in the problem in the denominator. So say for example, you were given meters and you are looking for that to be converted into centimeters, and we know that 1 meter is 100 centimeter. So we can write this either as 1 meter over 100 centimeter or 100 centimeters over 1 meter. Which form we will use? This is what is given to you. Okay? Meters multiplied by which form is giving you the desired unit or the unit you are looking for in your answer in the numerator. You are looking for centimeters. Which form gives you centimeter in the numerator? The second one, right? Here. So you use 100 centimeters over 1 meters. This form. Now you see, you can cancel out those two units and your answer will be having the unit of centimeters. This works every time if you work with the units. Sometimes in physics and chemistry, even if you don't remember an equation, if you can look at the units and you can figure out what you need to do with the quantities given. What am I given? What is my ultimate goal? How can I work through the units? Okay, this is so useful. So please do get a hold of this. Later onwards when you do problems, this is what you need. Dimensional analysis. I am not going to require you guys to memorize all the equations. That is not possible. I don't do that. Okay? You need to know how you can convert from one to another using the conversion factors. That will never fail. So this is how we use the dimensional analysis. Let's do an example. Say for example, I don't like this PowerPoints given by them because they just put everything in there. If we have step by step, that would have been helpful, right? We can work it and then check our answers. Anyway, say for example, we want to convert 8 meters to inches. Again, we do not have a straight conversion factor between meters and inches. So as I said, we will use 2 steps. First, you can convert the meters to centimeters. That's what the first step here is, up to here. If you look up to here, this is the first step. 8 meters, that's what you are given to. And your first goal is convert this to centimeters. So you write the conversion factor in such a form that centimeters is on the top and meters is on the bottom. So at this step, you are cancelling only meters and meters. So you have centimeters now. Now your second step is converting the centimeters to inches. So your goal is to get inches as your answer. So you put inches on the numerator and centimeter in the denominator. So now you can cancel this centimeter and this centimeter. So your answer has inches. And then you perform the numbers. Take out your calculator and what are you doing? 8 multiplied by 100 divided by 2.54 will give you 315. And here we need the answer in 3 significant digits. Even though you see this 1, please, when we take the conversions, those numbers are not actually part of the problem, right? The significant digits are determined by what numbers are given in the problem. So in the problem, it is given with not this, 8.00. That means these 2 zeros count towards the significant digits. There are 3 significant digits in this number, and that is why you have to answer with 3 significant digits. Questions so far? 8 multiplied by 100 and then multiplied by 1 divided by 254. Multiplied by 1 is exactly the same as that, and something below means you are dividing, right? So divide by 2.54 and you will get 315. You can check the calculations yourself. Well, this is not done by me. It's, as I said, the publishers, as you can see, this is not the slide which I make. They send it to me, and whatever mistakes I see, I would try to edit it, but certain things we will see only when we are in the class. Yes, I have already put chapter 1. Yeah, I have already put chapter 1 PowerPoints in the CM Connect.
This is what our quizzes will go by, exams and stuff.
Will it go by the PowerPoint or more the book?
You have to read the book. Don't think that PowerPoints will tell you everything. No. Matlab PowerPoints is showing you the key points or key ideas, okay? But that alone will not give you everything. As I said in last class, just coming and listening to the lecture is not enough. You need to read the book. I think that's the end of chapter 1. Questions so far? I have posted your chapter 1 homework problems also. Okay? So today we have finished chapter 1. That means your homework is due when? Next Thursday. Not next class. Next class would be on Tuesday. But your homework is due on Thursday. I will always give you 1 week from the finish day to finish your homework. However, don't wait until the last day to finish start doing your homework, okay? It would be good if you can do the homework after each class, whatever questions pertaining to that class, if you can do when things are still fresh in your mind, that would be the best thing. But anyway, don't just think that my homework is going to take only 10 minutes. Well, I shouldn't say that. Maybe some of you will take only 10 minutes, which is good. But please do give some time. Okay? Don't wait at the last moment and then realize that, okay, I have to scramble because I don't have time.
Those are online too?
No, you have to do them in a paper and submit to me. Not,
Online?
no, it's not an online software. You have to, the questions are from the end of the chapter questions. I just put the question numbers, that's all I put in there. So you have to take your book and see what is that, say for example, if you 1.26, I think, does anyone printed the homework problems? 1.26. 1.26 means chapter 1. You will go to the end of chapter 1. Let's say, where is chapter 1 end? Okay, so chapter 1 exercises starts in page number 31, and I think your first question is 1.11. So 1.11 reads as classify each of the following as a pure substance or a mixture, and if mixture indicate whether it is homogeneous or heterogeneous, and there are choices given. So that is your first question. That is page number 32. And the second question is 1.14. I think I marked my book when I was posting the questions. So those numbers means the end of chapter exercise questions.
So we write this on paper?
You don't have to write the questions, but you have to write the answers in a paper and submit to me.
Does it have to be typed?
No, it doesn't have to be typed.
So bring it to class on Thursday.
Yes, just bring it to the class on Thursday. I will bring a folder by labeled homework problems, and before you leave for the day, you will put that in my folder. That's all you have to do.
That's in the syllabus.
What is in the syllabus?
The homework problem.
Yes, it's go to CM Connect CHY 121 course. It's not in the syllabus. On the left side, you should see a tab called Homework Assignments. Click on that, and you will see. I think I have put already chapter 2 homework questions also. I think I just sat for half an hour and figured out what all questions I want for 2 chapters. But now focus on chapter 1. Finish chapter 1 questions by next Thursday. Okay? And bring it. Any other questions on homework or what to do? I know this is first couple of weeks. Any sorts of questions you get, general questions, don't hesitate. Just shoot. You're all good? So we can move on to chapter 2? Okay.
Is chapter 2 PowerPoint on CM Connect yet?
I don't remember. Did I put it there? Did you find it along with chapter 1?
I just saw general one.
Okay, then I haven't put it in there. I will go and put it by today evening or by tomorrow morning. Okay? Okay, so chapter 2 is atoms, molecules, and ions. So we are going to go into the fundamentals of the real chemistry. So far we were just setting up, for calculations and other things. We are going to go into little more details. So from early ages, philosophers used to wonder how everything is made of, what everything is made of, and they had various theories for so many ages, but until 19th century we did not really have a full picture. So in 19th century, John Dalton, a famous scientist, came up with a theory which is called the atomic theory of matter. And this theory says that atoms are the fundamental building blocks of all matter, and they are the smallest unit which would retain all the properties, all that stuff. So Dalton came up with his atomic theory. Dalton's theory has 4 important postulates. So only those postulates we will focus on. So the first postulate was each element is composed of extremely small particles called atoms. We have seen that in last chapter also, right? So atoms are very small and every element contains atoms. Now the second postulate is that all atoms of a given element are identical to one another in mass and other properties. But atoms of one element are different from atoms of all other elements. What do we mean by that? Let's say if you have oxygen, an element. If you take atoms of oxygen from anywhere on the planet, they are going to have the same mass and same chemical properties. That's what it means. But if you take nitrogen, the atoms will have different properties compared to oxygen. Let's say when we say fruits, if we compare fruits, let's say apples to oranges. If we say apple, but there are so many different kinds of apples, right? Which grow, I mean, if you overall look at the world in all countries, if you think about all the population of apples, there are thousands of varieties of apples with different color, different taste, different shape, different smell, but they are all apples. Similarly, if you look at another fruit, oranges, again, thousands of varieties, but they are all called oranges. That's not the case with two elements. That's what this postulate says. It doesn't matter. If it is oxygen, then it doesn't matter from where you are looking at it. Anywhere in the world, all oxygen atoms have the same mass and same properties. If you take another element like nitrogen or chlorine, it doesn't matter where you are looking at the sample, it will have the same properties and same behavior. That's what the second postulate says. The third postulate is atoms of an element are not changed into atoms of a different element by chemical reactions. Or in other words, atoms are neither created nor destroyed in chemical reactions. So we saw that physical change means it's just, liquid to solid to vapor. It's just like, states will change. But a chemical change means one or more new substances are formed. So do not think that, okay, new substances formed means there is a new element forming in a chemical reaction. Or the element you are starting with is destroyed. No, that is not the case. Okay? In a chemical reaction, no elements are destroyed, no elements are formed. Then what is a chemical reaction? That is what you might be thinking. Hold on that thought for a moment. Let's see the last postulate, that is the fourth postulate. The fourth postulate is that compounds are formed when atoms of more than one element combine, and a given compound always has the same relative number and kind of atoms. Okay, that we talked about compounds when we talked about the classification of matter. So when atoms of more than two elements combine, we have compounds. And a given compound will have always the same combination. That's what it says. That is, if you take water, a compound, it is always H2O. It's always the same composition, 2 hydrogens per 1 oxygen. That's what this postulate means. So,
I got that bottom part confused.
okay, bottom part, this?
Yeah, oxygen's supposed to be red and nitrogen's supposed to be blue.
That is right. That is a mistake. Usually oxygen is red and nitrogen is blue. They have labeled it different. Yeah, good catch. I didn't even look at that picture. As I said, the PowerPoints, they are not always perfect. And this one, since it's the new book, it's their new edition, and I actually don't like this set of PowerPoints. The last one, which I used last year, it was more colorful and, things went in like highlighted ink and all that stuff. It was really good. Well, some of the pictures have changed. The pictures are from the new book, so I don't want to put older pictures to you. And you will be wondering, where does this picture come from? My book doesn't have this. That is why I'm using the newer PowerPoints. I hope they will. I'm going to send my feedback that, whoever did the older PowerPoints, that person should do this. It's so, even you won't believe that red highlighting, I did that myself. It was all black. And I'm like, I want the keywords to be in a different thing so that when you look at a PowerPoint, you know what the keyword is, what you are looking at that PowerPoint, rather than just all black, letters. Anyway, what can we do? We have, limited resources, so we will work with that. So that third postulate we talked about, that is, atoms are not created or not destroyed. So what happens in a chemical reaction? This postulate comes from another law called law of conservation of mass. Law of conservation of mass says the total mass of a substance present at the end of a chemical process is the same as the mass of the substance present before the process took place. Or in other words, if you start with 10 grams of something, doesn't matter, two things together, 10 grams of something. After the chemical reaction, you have two new stuff, but if you take the total mass, it would be still 10 grams. Okay, that's what that law says. So what happens in a chemical reaction? The mass doesn't change. You are not destroying anything. You are not creating anything new. So what actually happens? The second line. During a chemical reactions, atoms are only rearranged. Okay, when we learn more in detail a chemical reaction, you will see that. Atoms get only rearranged, and when atoms get rearranged, we get new compounds. Like the periodic table lists all the elements we know, and again on the periodic table, everything we see in this world is mostly made of just 100 elements. But they are in different combinations and then they make different things. Just like in English alphabet, we have only 26 alphabet, but we have so many millions of words because alphabets are in different combinations in each word. That is why we have different words. Like, just like that. Just the atoms gets rearranged and we have a new compound. That's what happens in a chemical reaction. So we are not destroying anything, we are not creating anything. So now we are going to look into subatomic particles. There are several subatomic particles, but we would focus only on these three. That is protons, which are positively charged, neutrons, as the name suggests, they are neutral, no charge, and electrons, which are negatively charged. And before we discuss into the discovery of these subatomic particles, we should remember this principle, that is, same charges repel each other, while opposite charges or unlike charges attract one another. Okay, that is the basis, or based on this principle, we figured out what is the charge of each particle and what they are. So, the first subatomic particle discovered was the electron. Now, a little bit history on how the electron was found. Again, J.J. Thomson is a scientist who is credited for the discovery in 1897. So if you can look at this picture, what it does is, here is a glass tube which is coated with a fluorescent subject so that you can see the beam of rays passing through, and you have the negative electrode and positive electrode. The name of the negative electrode is cathode and name of the positive electrode is anode. That is basic terminology in a battery. If you have seen physics or anywhere, if you have looked at batteries, that is how you label them. The positive electrode is anode and the negative electrode is cathode. So, and if you apply a potential, you will see that a beam of rays pass from cathode to anode. So the rays are usually not, like colorful or anything. So just to identify the rays, that is why you have the glass which has a fluorescent material so that you can see the rays. Now, electrons move from the cathode, that is the negative electrode, to the anode, the positive electrode. The tube contains a glass screen that fluoresces, showing the path of cathode rays. Now, cathode rays means the rays originated from the cathode. That's what it means. Now, we see that if these rays are disturbed by a magnet, like if you take a powerful magnet to this path of these rays, they get deflected. Okay? Hold on to that thought. So, when they observed that, they did further experiments. Of course, Thomson did further experiments. So, this is his famous cathode ray tube experiment. What he does is, once again, you have now, here is a cathode, the negative electrode, and here is the anode, the positive electrode, and the positive electrode has a small hole in it. So, the cathode rays are formed and then they pass through this hole and they travel, and here is the fluorescent screen. Okay? Now, just imagine if you do not have any electric charge or magnetic field around it, then this rays would travel in a straight line and hit the fluorescent screen. Now, if the magnetic field and electric field, if they are exactly cancelling each other, then also the rays will just go in a straight line. What about if I just take this magnetic field away? When Thomson took the magnetic field away, he noticed that this beam was bending towards the positive electric field. What does that mean? Whatever that beam was made of, it was made of negatively charged particles. Remember, opposite charges attract each other. Same charges repel each other. So if it was bending towards the positive electrode, means positive plate, means the beams themselves were negative. And of course they were not going here because that is negative and negative, they repel each other. Okay, so then further he did a lot of more experiments. We are not going to go into the details of that. And he measured the charge to mass ratio of an electron to be 1.76 into 10 to the power 8 coulombs per gram, and that number is not significant. Then another scientist, Robert Millikan from University of Chicago, he did this experiment called oil drop experiment, Millikan's oil drop experiment, and determined the charge of an electron, the actual charge of one single electron. And it was determined to be 1.602 into 10 to the power negative 19 coulombs. Now how he did this experiment, again we don't go into the details, but just a general idea. This is kind of a cross section of this vacuum tube. He has this tube where he spray fine mist of oil drops, and then here is the positive plate and negative plate, and the positive plate again has a small hole, so the oil drops are coming in, and here you have a beam of X-rays hitting on the oil drops. So the oil drops would absorb extra electrons from the X-ray, and they will kind of start falling into the plate. But remember, this is negatively charged. So the oil drop, as it reaches the negative, if it has extra electrons, now each drop is also negative, right? Because it has extra electrons on it. Electrons are negatively charged. So now if you visualize that oil drop is kind of negative in nature. So as it comes down, this plate is negative. So what happens? Would the oil will stick? It would kind of bounce back, right? So he adjusted the electric current, and he kind of calculated exactly how much power it would take to suspend an oil drop right in the middle. Okay, so from there he calculated the charge of the single electron. Again, luckily we are not going into the details of those calculations. We don't need to know those. It's good that somebody did that for us. And the charge has been calculated as 1.602 into 10 to the power negative 19 coulombs. Again, this is a constant. You don't have to memorize this number either. If you have to use this in a calculation, this will be given to you. Okay, this is a constant. Now before we discuss about, so that was about the discovery of electrons. Before we discuss about the discovery of protons and neutrons, we need to understand a little bit about radioactivity. So what is radioactivity? Radioactivity is the spontaneous emission of radiation by an atom. So you don't do anything. If you just keep the material, it is emitting some kind of radiation. So it was observed by Henry Becquerel for the first time, and then of course these two famous scientists who won the Nobel Prize for the discovery of radium and studies on radioactivity, Marie and Pierre Curie. Among various radiation, these are the three main types of radiations found in radioactive substances: alpha particles, beta particles, and gamma rays. If you take a radioactive substance, let's say here, right here in the middle, there is a radioactive substance, and it's emitting rays, so you are kind of directing that rays to a hole, and then again put an electric field, a positive and negative field. See what happens. One particular type of rays are bending towards the positive plate. That means those rays are negative, and we call them beta rays. So beta rays are negatively charged. Now, there is another type of rays which are bending towards the negative electron. That means the rays themselves are positive and those are alpha particles or alpha rays. Now there is another kind which goes straight. It doesn't do anything towards positive or negative. That means it has to be neutral. It doesn't have any charge and we call them gamma rays. So these are the three major types of radiation we will see in radioactivity. Now, so Thomson came up with this electrons, so they knew that at least one subatomic particle called electron and that is negatively charged. So now he is coming up with, okay, so how an atom would look like. So he put across this famous theory called plum pudding model of an atom. It is basically, he said, here is an atom which is in spherical shape, and when he calculated the mass of an electron, it was so small, so he thought, oh, when compared to the total size of the atom, electrons do not contribute much. So he said, electron is this big positive sphere and atom is this big positive sphere and electrons are embedded on the surface like plums on a pudding, like raisins on, some pudding surface or something like that. So that is what he said the atom would look like. Now, they knew that this sphere is positively in nature because overall an atom is neutral. So we know that electrons are negatively charged and overall the atom is neutral means there has to be something which is positive, right? So he said the entire sphere that's positive and electrons are just sitting as plums on the surface of the atom. So everyone didn't believe that, of course. So Rutherford, he decided to test Thomson's theory. So he take a gold foil right here, and he bombard this gold foil with a beam of alpha particles. What is the charge of alpha particles?
Positive.
They are positively charged. Okay. So what would you expect if Thomson's model is correct?
It would stick to the electrons.
Look at the Thomson's model one more time. Here is Thomson's model. He says all you see in pink, that is all a positive charge spread throughout the sphere. And now you are going to hit this with alpha particles. What would you expect? They should all bounce off, right? Because this entire sphere is positive, alpha particles are positive, so it should bounce off. That's what you would think. But actually what happened? You saw different things. They saw that, well, some of them bounce off, but not like you thought, not like a U-turn bounce off, kind of towards the sides, and some of them actually came through. Look at this. So that means that plum pudding model was not correct, right? So since some of them deflected and some of them came through, the model could not be correct. So what actually happened? There is this new model called the nuclear model of atom. So once again, let's think about this is a part of the gold foil. Can you see like where I'm doing the pointer? This is a gold atom. Okay, so each of them are gold atoms. Now each of this atom, at the center there is a dot called nucleus. Whichever alpha particle hit on the nucleus, they actually bounced. Based on how they hit the nucleus, they bounced either in a large angle or in a small angle. The particles which did not hit the nucleus, like this one or this one or this one, they just zip through the foil. What does that mean? Whatever positive charge you have in the atom, it is focused on a very small area called nucleus. So alpha particle which is positive, it's hitting the positive core called nucleus. So positive, it's bouncing back. Other alpha particles which are not hitting the nucleus, they are not bounced by anything. So they just zip through the atom. So that was the result. So, yes?
So
Well,
There's two different ones.
there are two different ones. Once again, let's say this one was hitting the center of the nucleus. So it kind of, really bounced back. This one was, if you say, it kind of, touched the nucleus through the periphery.
Like the
So,
second line down kind of.
yeah, there, this one. So it's just touched, so it is deflected a little bit,
The bottom.
but yeah, but not much. Okay. The idea you have to take here is we don't have to worry about how they deflected. We have to worry about, okay, so there was this positive core. Whichever alpha particle hit the positive core only got deflected. Other ones passed through. Yes.
So that's saying that every nucleus is positive.
Every nucleus is positive. Yes, that's what it says. Or not nucleus is positive. Whatever positive charge you have in the atom, they reside in the nucleus. Okay, that's what it says. So Rutherford came out with the nuclear model, and he said a very small dense nucleus with the electrons around the outside of the atom. So the plum pudding model is gone now. There are no big sphere with electron plums on it. Now it's going to be a very small seed called nucleus with all the positive charge, and the electrons are just around it in a cloud. So if you look at an atom now, this entire atom, here is the nucleus, and that contains the protons and the neutrons. Neutrons doesn't have any charge, so the nucleus contains both protons and neutrons, and then the electrons just spread around the space, so they occupy a larger volume. So if you compare, look at the size of the nucleus, such a small thing, whereas the total size of the atom could be 1 to 5 angstroms. So most of the volume of the atom is an empty space. Means again, it doesn't mean that when you see a cloud like this is all filled with atoms like this. Okay, when you learn more in detail on the atomic model, you will realize this is like a probability map. This is at given time, where can you find the electron around the nucleus. So this is a probability map, not like every single dot is a electron. Okay, so the other subatomic particles, protons, were proposed by Rutherford in 1919, and then later in 1932, neutrons were discovered by James Chadwick. So all three subatomic particles are discovered now. So here is a table which summarizes their properties. So again, protons and electrons are the only charged particles, and neutrons have no charge, and protons and neutrons contribute to the mass of the atom. As we said, electrons are very small. The mass of an electron is very negligible. So the overall mass of the atom comes from the mass of the protons and its neutrons. So we are not even going to learn these numbers. Don't worry about these numbers either. What you have to remember is now here. One proton means it represents one positive charge, and one electron means it represents one negative charge. That is important. And neutron, no charge, it's neutral. Okay, so now onwards, when we say one proton, it's one positive. Two protons, two positive. 10 protons, 10 positive, so on. Now we are going to look into the symbols of elements. Well, before I go there, any questions so far on subatomic particles, their discovery? As I said, this is just the history. You are not going to calculate or describe how they did all those things, just to be aware of it. All you have to carry forward from there is the three particles, what are their charges? Everyone is good? Okay, so let's look at the symbols of elements now. So elements are symbolized by one or two letters. If you look at the periodic table, most of them have one letter or two letters. That is how we symbolize an element. So say for example, let's take carbon, which is one of the most abundant element on earth. And if you take carbon, the symbol of carbon is just C. Carbon starts with a C, right? Okay. So how about calcium then? Calcium also starts with a C. So can I use C for calcium also? No. So we will have a confusion there. Therefore, we are going to add the second letter of the name. So calcium would be Ca. That is the trend for most of the elements. Like the first one, it will be the single letter. If you have another one also starting with the same letter, then we will add the second letter also. But then we will see elements like iron. Iron, the spelling is I-R-O-N, but the symbol is not I-R, the symbol is Fe. Or silver, the symbol is Ag. Gold, the symbol is Au. So, how do we explain those? There are some elements whose names are derived from its original name, the Greek name or the Latin name. Silver is called argentum in Latin. So the symbol is Ag, not Si. Okay. Sodium, the symbol is Na. It is, I think it is natrium. That is the name of sodium in Latin.
So if I knew from Latin right now, I'd be pretty sad.
Well, if you know the names, yes. Gold, it's called aurum. A-U-R something. So it's Au. Mercury, hydroargentum. Symbol is Hg. So there are some elements. Iron, as we started with, iron's Latin name is ferrum. That is where we get Fe. So there are some elements whose name and its symbol does not match. So that time you remember they come from its Latin name. Otherwise, usually it's the first letter or first two letters for the name and symbol. Now, we see some numbers also on the periodic table. We are going to understand what are some of those numbers. So, the first number we are going to work is called atomic number. Atomic number of an element. Atomic number of an element means it is exactly the same number as the number of protons and number of electrons in a neutral atom. Okay? So all atoms of the same element will have the same atomic number and therefore same number of protons. So if you take oxygen, you will see that its atomic number is 8. It doesn't matter oxygen from United States or oxygen from China or oxygen from Europe. They all have 8 protons. Therefore, the atomic number is going to be 8. This is what I tell my students. Think of atomic number as the social security number of the elements. If you change the number of protons or the atomic number of an element, you are changing the identity of the element. Okay? So every element has a specific number of protons and that is the atomic number. Now we are going to see another number which is called mass number of an element or mass number of an atom. So the mass number is the total number of protons plus neutrons, not protons plus electrons, protons plus neutrons. Okay? So that is called the mass number. So if you look at this, this is the way we represent this. We take the symbol on the left side as a subscript, we write the atomic number. On the left side as a superscript, we write the mass number. And mass number is the number of protons plus neutrons. Of course, atomic number is just the number of protons. And a neutral atom will always have same number of protons and same number of electrons. That is the meaning of the word neutral, right? If there is a discrepancy between protons and electrons, would the atom be neutral? It will not be, because protons are positive, electrons are negative. If those numbers are not equal, then there will be either positive charge or negative charge in the atom based on what it has extra. So in a neutral atom, positive numbers and negative numbers are exactly the same. Now this is the most common way of representing the symbol, like with the 6 and 12. However, we can write this way also, that is So if I want to write the full name, I can write carbon-12. We don't usually write the atomic number because carbon means carbon can have only one atomic number, which is 6. That is understood. But mass numbers can change. That is why that you will specify. Okay? So that is another way of writing the symbol. Now we are going to see what do we mean by changing mass numbers. Isotopes, a new name. So isotopes are atoms of the same element with different mass numbers. As I said, mass numbers can change. So how can we have the same element, different atoms, and different mass number? Different number of neutrons. Good. We already said that atoms of one element, it doesn't matter regardless of where they are all going to have the same number of protons, right? And whatever situation they are going to have the same number of protons. And we said mass number is protons plus neutrons. So atoms of the same element with different mass number means, of course, the changing thing or the variable is the number of neutrons. So when the number of neutrons change, the mass number also will change. Here is an example of various isotopes of carbon. See that the symbol is, as I said again, if you are writing carbon, then it is assumed that it has 6, not assumed, it is known that it has 6 protons. So you don't have to write that 6 as the subscript, but you will write the mass number. See the first one, C11, means it has 6 protons, it is neutral, so it has 6 electrons, but there are only 5 neutrons. So how do we know that? 11 minus 6 is 5, right? So similarly, carbon-12, atomic number of carbon is 6, that means there are 6 protons. So how many neutrons there are? 12 minus 6, 6. Similarly, carbon-13, atomic number of carbon is 6, so that means 6 protons. So the neutrons has to be 13 minus 6, 7. Similarly, for carbon-14, there are 8 neutrons. Okay? So isotopes, these are all called isotopes of carbon because they have different number of neutrons. They are all atoms of carbon, but they have different number of neutrons. Question so far? If you don't stop me and ask me a question, I would assume you are all following me, okay? As I said in last class, anytime feel free to raise your hand, stop me and ask a question or ask me to repeat. Okay, do practice exercise 2.2 now. Probably that has something to do with isotopes, I believe. So, let's open the book and get 2.2. Please do bring your book to the class because from now onwards we will have problems in between, okay? I do not want to do just the lecture alone. It would be helpful to do kind of practice problems in between. So 2.2 reads as, well, practice exercise, that's what we have to do. So the question reads as, how many protons, neutrons and electrons are in A, barium 138, an atom of phosphorus 31. Even though we have the answers there, let us try to understand how do we do this. That's what we need to know, right? Okay, so first one is barium 138. So this is what is given in the problem. So remember the number we write here is the mass number and the symbol is barium. So look at the periodic table and tell me, so we need to write what? Protons, electrons and neutrons? Yes. So we need the number of protons, electrons and neutrons. So how many protons barium has? How do we know that? Look at the periodic table. And what is the atomic number of the barium? Number 56? Okay, the number you see above the symbol in the periodic table, okay, that is the atomic number. So that is the same as the number of protons. So we say there are 56 protons. And how many electrons? The same number, because the atom is neutral. That means it has to have the same number of electrons.
Always the same.
Always, if it's a neutral atom, the number of protons and electrons has to be the same by definition. Otherwise, it's not neutral. So, now we need to know how many neutrons we have. How do we figure that out?
138 mass.
So, remember this 138, this number is protons plus neutrons, right? And we know that there are 56 protons. Therefore, 138 minus 56 should give you the number of neutrons. 82. Is that the answer from the book? So now you know how you got that. Right? Okay, now let's do the second one. It says what? P31, phosphorus 31. The symbol of phosphorus is P. Now, when we write the symbol hyphen a number, what is this number? Is this the atomic number? It is not the weight, it is the mass number. Okay, because weight will come in a few minutes. That will be different from mass number. So when we write like this is the mass number. Okay, so this number is again protons plus neutrons. So we need the number of protons. Phosphorus. What is the atomic number of phosphorus? 50? 15. Okay, therefore how many electrons? 15. How many neutrons? 31 minus 15 would be 16. This is how you calculate the 3 subatomic particles in an atom. That is, if you are given either mass number, you need the mass number, that is correct. If you are given the mass number and then just the symbol, you can calculate everything because you have the periodic table, and looking at the symbol, you can figure out what is the atomic number, which is the same as number of protons and number of electrons.
So 16 is the atomic number?
16 is the number of neutrons. Yes, atomic number and number of protons would be the same. Now, where is that dot? Okay, now the next thing is atomic mass. We'll just talk about atomic mass and we will stop. So, for an atom, so we already see that there are isotopes, that is, the mass number is different because there are different number of different number of neutrons. So that means if you take 2 isotopes of an element and if you go exact mass, that might be a little bit different. Okay, the masses might be a little bit different from one another, and we have instruments like mass spectrometer which can calculate the exact mass of one single atom. Okay, so say for example in this picture what it shows is you put a sample of chlorine into it, and I'm not going to explain how mass spectrometer works now, you don't need to know that, but mainly it would ionize the sample, and the samples are passed through a strong magnetic field, and the magnetic field will differentiate atoms with different mass. Okay, so as you can see, after it passed through the magnetic field, the Cl37 and Cl35 both are chlorine, and those are the 2 major isotopes of chlorine, one with 35 mass number, one with 37 mass number. That means one has more neutrons than the other. So based on that slight mass difference, they will separate and they will pass through the detector as 2 different beams. So we can collect it differently. So we have mass spectrometers. Using that we can separate and calculate the mass of a single atom. However, where is that dot? Okay. What we do is, in real world, we are not using one single atom of something, right? We are using large quantities. Actually, like a spoon of something if you take that has so many atoms, it's beyond our imagination. When we talk about a mole quantity, we will understand that. So in real world, since we use large amounts, we actually use average masses in calculations, and that is what is called the average atomic mass. An average atomic mass is calculated from the isotopes and element weighed by their relative abundance. What do we mean by that? Here it is. So we have different isotopes for an element, and we need to know their abundance, like what percentage of that isotope exists. If we know that percentage and the isotope mass, we can calculate the average atomic mass. This is the equation. That is, relative atomic mass is going to be mass contribution from the first isotope plus mass contribution from second isotope, plus if you have a third isotope, then mass contribution from the third isotope. And how do you calculate mass contribution from one isotope? The isotope mass given multiplied by its relative abundance. Relative abundance will be given in percentages. Do you want to do one problem on that, so that this is just, okay, let's just do this problem and then stop it. So that is 2.4, which is in page number 48 of your book. So before we do the practice exercise, let's maybe look at the sample exercise, which is worked out in the book. So that would make it clear. So the sample exercise reads as: naturally occurring chlorine is 75.78% chlorine 35, and its atomic mass is given to you in AMU. AMU means atomic mass unit. And then 24.22% chlorine 37, again atomic mass is given to you, 36.966 AMU. Calculate the relative atomic mass or the average atomic mass. Look at what we have done here. Atomic mass given multiplied by its relative abundance. Remember, percentages, when we use percentages in calculation, we cannot use it straight away. We have to convert that to decimal points. That is something you learned in math classes, right? So 75.78 will become 0.7578. So multiply those two quantities, you get the relative isotope mass of chlorine 35, and then the next two quantities will give you chlorine 37, and just add that. So you get 35.45, which is the relative atomic mass of chlorine. Now let's do the practice exercise. So there are three isotopes of silicon: silicon 28, silicon 29, and silicon 30. We are given the percentages and we are given the AMUs. We need the atomic weight of silicon. So the first one is silicon 28. What is the percentage? 92.23. So convert that to 0.9223 decimal point, multiplied by, what is its AMU? 27.97693. 27 point, could somebody repeat that number?
963.
96.
Right?
No, I think there is 97 693. Okay, so that will give you the isotope contribution of Si28. Now we need similarly Si29. What is the percentage? Are you saying the number here? No, I'm talking about Si29. What is the percentage? Convert that to decimal number, please. 4.68. That means it has to be 0.0468. You know how to convert from percentage to decimal number, right? All you have to do is divide by 100, because percentage means per 100. Cent, century for 100. So percent per 100. So you just divide by 100. That is how you convert this. Okay, multiply this by its atomic mass, which is 28.97. Okay, 28.97649. Okay, Now the last one, SI 30. What is the percentage converted to decimal? 3.09. Just divide that by 100. So 0.0309, right? Multiply that by its AMU, which is 29.97377. Okay, so finish those calculations and let's get the numbers here. What is the first number? As I said, guys, everyone please bring your calculators. We will be doing problems in class, okay? And you don't want to just sit there and watch me doing the problems. You have to do it yourself and check the answers to get this material. You will think, oh, okay, she's doing everything, it looks good. But when you are on your own, so please do it on your own. Bring your calculators. So what's the first number when you multiply? What do you get? First of all, if you are expressing these numbers, how many significant digits should be used? 4, because this one has only 1, 2, 3, 4, and in multiplication and division, remember, the least number of whichever number you use, the least number of significant digits will be used. So give me the answer in 4 Sig.Figs for SI 28. 25.8. What is it? It's only 3 now. I need 4. It's a 0. What is the next number? 3. Then we will just keep it at 0. Okay. Now let's do SI 29. What is SI 29s? Again in 4 Sig.Figs. Multiply these two numbers and what do you get? 1.356. Last one. 0.926. That's only 3. 3, 1.
Or 2.
Why it is 2? 1 or 2? We have to be specific. What was the next number? 9. Then it has to be 2. Okay, now you add those 3 numbers and you should have the relative atomic mass. When you add those 3 numbers, what do we get? Are we getting 28.09? Has to be. Do it for yourself and make sure. If it is not, then you made a mistake in one of those calculations or round offs. Are we getting 28.09?
28.08.
28.08. That's what you get? 0.85. So 5 has been cut off and added because we have to keep it at 4 Sig.Figs. That is how you get 28.09.
I must have hit something wrong because I got 082.
Okay, then there must be something in somewhere wrong. So this is how you calculate the relative atomic mass.
When you add those numbers like this, it's 28.08.
That's right.
Okay, then when we rounded off somewhere here, we made a mistake. Or okay, there could be another chance. I can tell you this. There could be another chance. Maybe the person who did the calculation, they did not round it off in each step. They kept everything, and at the end they came and round off only the last answer. That could be another reason.
Would that work with you or not?
That would be fine. It would be fine. Okay, I think we have to. That's fine. We are getting out. You can come in. So guys, let's just stop right here.